QIMC. Welcome it. So they should.
Good morning. My name is Edward Position. Before I start, I would ask since the classification of natural white hydrogen is still ongoing, serious government review, that we will defer questions concerning the regulations. And we would suggest that you contact the people at the government to get your answers. Now, what I want to do today is show to some people who know less probably than I, that hydrogen has many uses, ranging from oil refining, fertilizer, and ammonia production, methanol production, and food production. And more increasingly today, it's used as a low carbon fuel for transportation and manufacturing, for the power generation and storage of excess electricity, for steel and cement production, and for heating. The demand for hydrogen in 2020 was estimated to be 86 million tons, whereas in 2050, the demand is expected to grow to as much as 580 metric tons. To meet the market demands, hydrogen is being produced from oil and methane using heat and steam, or by electrolysis of water using renewable energy to break the water molecule to release oxygen and hydrogen. The industrial processes used to produce hydrogen also produce carbon dioxide and other carbon emissions in the amounts ranging from 1 kilogram to 9 kilogram CO2 per kilogram of hydrogen. To indicate the amount of carbon that is contained in the manufactured hydrogen, industrial gas is graded by color: gray, blue, and green. The cost required to remove CO2 from the manufactured hydrogen ranges from $2.12 to $640 per kilogram of hydrogen. The cost to produce natural white hydrogen that occurs naturally in nature is approximately 50 cents per kilogram. The government have clearly indicated that the source for clean energy, such as wind, hydrogen, etc., need to meet the 2050 environmental CO2 emission target. White hydrogen clearly meets these requirements, and today is the cleanest and least expensive source of energy. Natural white hydrogen, being considered, is produced naturally in the Earth's crust and is continuously being produced. The geological processes that generate significant quantities of hydrogen are oxidation of magnetite and mafic minerals, radiolysis, maturization of petroleum products, and mantle degassing of gases, mantle-derived basic intrusions, and volcanic rocks. Consequently, there are myriad amounts of data, observations, and knowledgeable facts that must be recognized and must be interrelated as we contemplate exploration. Geologists construct a carbon visual model to visualize the spatial interrelationships and the geological processes and the settings in which hydrogen can accumulate. Although these models are predictive, by the very nature of construction, they can be biased, and as additional observations are added to the models must change. Now, what I'm going to show are two models, what we call Earth hydrogen factories, that show the attributes that must exist in an area to be the source of natural hydrogen. As you can see, we need highland from which water can be drained and focused into the crust. We need the correct source rock from which the hydrogen can be produced by the oxidation of mafic minerals, iron-bearing minerals, and iron-bearing rocks. We must also see other processes that also tend to produce hydrogen. And above all, we must understand the fracture and geological travel systems in which hydrogen takes to reach surface again as it becomes absorbed into water molecules at critical conditions. The water must rise, or does rise, to the surface and finally dissolves the hydrogen into the atmosphere. So we can see these tracks. Now, I'm not going to belabor the other consequences, but it's just to show you that, that there are many attributes that must exist in the area when you choose to do exploration there. And we find that Nova Scotia meets all of these attributes indicated in the model. In this map, we see the structure and location of the carbonate sedimentary rocks that onlap onto the continent of North America. These onlapping sediments are shown in gray, and you can see that northern Nova Scotia, the sediments are overlapping onto continental crust. In this area, the continental crust has been an intertectonic basin has developed during the tectonic period with Naduma territory shown in brown from the European continent was welded against the North American continent and created these intertectonic bases, of which Cumberland Basin is one. The second requirement is that the rocks underlying the intertectonic basin must have the correct temperature, must have the correct composition and mineralogical content so that they can release by oxidation the oxygen contained within these minerals. And we can see that the Avalon Peninsula, which underlies the intertectonic basin, is composed of highly metamorphic granitized rocks, providing the potassium-bearing minerals to produce electrolysis, and it also contains uranium thorium for the electrolysis. But above all, if water enters these compositional basins and interacts with the biotite contained, or animals contained within these crustal basement rocks, they have the correct composition to release the hydrogen. The second requirement that it must happen is that the surface waters must infiltrate into the basement rocks if they are to produce hydrogen. The Cumberland Basin is located between two basement uplifts called the Cobequid Highlands on the south side and the Hastings Uplift on the north side. These uplifted highlands created the topographic conditions that allow the water to flow from surface into the basin. A major syncline plunging shallowly to the west was developed early in the structural history of the basin, of the Cumberland Basin, and exposed permeable sedimentary formations dipping into the center of the basin. And these dipping formations had the correct porosity and permeability structure to channel the flow of surface water into the basement rocks, where again they initiate oxidation of mafic minerals and iron-rich rocks to produce quantities of oxygen. Following the deformation of the basin, a variety of subparallel faults and fold structures were developed. These structures provide the flow channels that control the upward convective and diffusive migration of hydrogen-laden fluids and gas toward surface. However, some of the hydrogen was trapped by impermeable layers that overlay domal structures. Yet, native hydrogen continued to surface, eventually into the atmosphere. It populates the structures along the way in porous formations and eventually reaches concentration in some soil covered samples. Understanding the structural framework that hydrogen took on its way to the surface is essential if we want to know where the locations are located in which hydrogen can concentrate to form large accumulations over larger areas within the basin and have the correct economic attributes that lead to their extraction. Let us examine some of these structures that now appear at surface. In this diagram, we see from Walden, that was taken from Walden, that the internal basin is loaded with structures and faults and folds. The later deformation occurred during the continental collision, warped the syncline basin and formed two distinct secondary basins called the Eight-Dot syncline and the, let me get that pronounced right, Tadamagush syncline. Again, the south part of these synclines remained simply dipping, but slightly folded, whereas the northern contacts were highly deformed by faults and folds, and the folds were narrow anticlines that contained truss faults and slipped the basal formations to surface. Some subsequent northerly trending faults broke these secondary anticlinal structures and block outputs resulted in which the basement rocks again were exposed. So, to summarize briefly, we have the required structures and the required ecologies and the required formations that will lead to hydrogen being concentrated in the Earth's crust. And this is partially the reason why we chose Nova Scotia to be the source of our exploration program. The area we chose is the western part of the syncline, and you can see our location of licenses that are located basically along the southern contour of the basin with the overlying basement rocks of the Cocoa Highlands, and the plains extend southwards over the fault of the Spiral Cove area, which are overlain by basal rocks that contain the right conditions for storing hydrogen. The western part of the basin area was therefore staked along these faults and poles. Many of these structures and the main Chetawuk fault zone have now been shown to partially or entirely control the effective transfer of hydrogen and the radon-toron values that are currently being measured in the field. Transfer zones along these oblique structures are also now being located by LiDAR radar satellite and recently have by initiated geophysical studies. Extensions do occur in this area along the faults, and these are associated with normal faults in the transfer zones of the fault and this again extends the structures in which accumulation of native hydrogen can occur. Now let's go into the progress we have made since we started the project less than a year ago. A well-planned and sustained exploration program normally proceeds in stages or in phases. Each phase has a defined objective that needs to be completed before a new exploration activities are undertaken. This approach allows the QIMC to undertake an extensive and comprehensive review of the data that was acquired prior to selecting the area for drilling and correlate these results to desired objectives. For an example, the presence of high nitrogen anomalies and in the till soil samples have been observed to occur in presence of faults. If the results are not clear, however, it may be necessary to undertake additional exploration activities to achieve an even more intensive and comprehensive understanding of the structures, because it is the structures that control the flow of nature of hydrogen in the area. More extensive data acquisitions from geophysical and seismic surveys, database compilations, and the processing of the interpretations of these data may be required before proceeding to the next phase of exploration. So let's review what we have accomplished. The QIMC has now completed phase 1 of the program. Relevant data has been compiled, evaluated, and recorded on a preliminary database that is still being developed. The areas that may contain hydrogen-bearing targets have been thus identified, and the ground staked to begin the exploration program. Phase 2 of the program is nearing completion. To more locally locate the areas where hydrogen accumulations may occur, a hydrogen and radon-boron soil gas field sampling program was undertaken on the road networks that cross the area. The soil gas sampling determines how much hydrogen is present in the tail soil and in water. These studies are now nearly complete and have identified fairly substantial high hydrogen anomalies. Several field tests were also carried out. These studies have confirmed that the samples taken along the margin of the road and those taken in the undisturbed areas adjacent to the location of these samples on the road contained approximately equal amounts of hydrogen. This validated the equivalence sampling process that we carried out on the road network. Secondly, that pit on the Eatondale Road, from which road material was extracted, exposed flat-lying rocks of the Popovit Highlands, flat-lying sedimentary formations, shales, and high chloritic siltstones. On top of this, a vertical 2 to 3 meter vertical section of overlying unconsolidated material was also exposed. We took samples both at the exposed rock formations at the bottom of the pit and samples at the top of the soil horizon. Both sampling sites yielded similar results. This again confirms that results from soil gas sampling measures the amount of hydrogen coming from the rocks underlying the surface. Again, no faults, shear zones, or deep fractures were observed to occur in the rocks formations on the floor of the pit, which could have produced an advective flow of hydrogen to the surface. Yet highly anomalous values over 1,000 ppm for both hydrogen and Similarly, for radon, toron values were obtained at both the pit floor and the surface area. These data indicate that the fault structures may not be necessary to transfer hydrogen from the basement to surface. These results indicate and confirm that hydrogen and radon values in soils do measure the amount of hydrogen in the underlying rock formations. I'll show you a slide about the soil profile. You can see the top hill sample overlying the regolith, overlying a highly weathered surface, and these kinds of profiles are often preserved in Nova Scotia, where elsewhere they are completely scraped off the exposed rock. So we have another measure that confirms and saw that the hydrogen effectively flows to surface to collect in the surface samples. Since outcrops in the region are normally scarce, and the structural relationships between faults in the area result in poorly understood structural networks. As a result, additional detailed geophysical surveys are being contemplated and being undertaken to more accurately locate the characteristic fault orientation of the characteristic fault system present under the sites that contain high hydrogen and radon anomalies. In the West Africa area, for an example, results obtained in July during hot weather conditions were recently resampled in early November. Measurements in November returned hydrogen concentration as high as 3,800 and 4,300 ppm. These extreme high values closely match the high values obtained in July. This is unusual. Results normally obtained when weather conditions are colder and more humid are at least an order lower than the values obtained in the warmer summer weather. This again suggests that strongly adaptive flow systems are not necessary to transfer hydrogen to the surface, but can diffuse through rock formations and collect from rock formations that overlie a substantial collection of gases, of hydrogen gases. A radon survey, conducted over the Eastville Road west of the Advocate area showed that the maximum values in this surveys match the location of hydrogen maximum values, indicating that the survey methods used effectively locate zones of higher permeability associated with a secondary fault. That is, they help us locate the fault systems that are highly buried by debris. Areas having high radon concentration greater than 100,000 becquerels per cubic meter and elevated radon-toron ratios have been interpreted to indicate that the inductive system that brings the hydrogen to surface is deeply sourced, giving toron with its short half-life of 55.6 seconds, comparable to radon with a half-life of 3.8 days, enough time to be relatively depleted along the route to surface. So again, we have some indication of where the fluid is coming from. Exceptionally high hydrogen values, frequently over 1,000 ppm, have been obtained during the soil survey, taken along roads at many locations. In some areas, these highly anomalous hydrogen values are extended over narrow widths at 100 meters or so, whereas in other areas, anomalous values could be traced over several kilometers. In most instances, these high values appear associated with the presence of easterly trending shear fault systems. Future studies, however, must continue to detail the knowledge base that is present in the area. Now let us look at the results obtained. These are taken from press release reports and show roughly the area that was sampled. In the first picture, we see west Advocate area, and you can see from the graph shown that where the values greater than 200 parts per million are located. Normally, we consider values greater than 500 to be anomalous, and we don't see very many low value numbers. Now, the regrowth similarly shows exactly the same profile. So this indicates an extremely high rich area in the source area of hydrogen that is leaving the surface and constitutes the reasons that it must be drilled to verify the results. The second area concerns the East Advocate area, and again, the results indicate very high values, exceptionally high values, indicating that this area indeed needs to be explored for native hydrogen. Advocate Harbor to the south shows it's an area that is metamorphosed by mid-Jurassic to Triassic intrusions in the rift zone separating Nova Scotia from New Brunswick, and thereby posing a high thermal gradient into the area. Also shows that the rocks associated with these rift areas, dive-based dikes, gabbro intrusions, etc., also are leaking high concentrations of hydrogen, and again, indicating a completely separate source for hydrogen. The third area that we have decided to sample, decided to drill because of the results, okay, is the Southampton area. 5 profiles were measured, and the indications are that these values over a few thousand parts per million are present throughout the area. And again, I'm not going to belabor the point, but I think we can firmly say that this area is also highly anomalous with respect to hydrogen and needs to be drilled. The last area that we have time and the money to drill is the Spring Hill area in Nova Scotia. There we are showing two separate areas. One that you see on the north is QIMC property, whereas the area roads on the south side belong to QIMC, and they too indicate the values that are anomalous. So the Little Fork area is a very high value of 40,000 parts per million. And again, several samples over narrow zones of over 500 parts per million, which is considered to be strongly anomalous. The Salt Spring sections, okay, in the Spring Hill area, also preliminary services show several areas above 200 ppm for hydrogen, and again, local narrow zones that contain over 500 ppm. So now we have identified the areas. Where are we at with the exploration program? As mentioned earlier, phase 2 exploration activities are nearing completion. We have identified the targets, and now we are moving to locating diamond drill holes to determine if the underlying formations have the porosity and the ability to store required accumulations of hydrogen, and if the intersections of core contain structural characteristics that are required to promote effective flow of hydrogen throughout the area. The purpose for drilling is also to measure the flow rates of the natural gas for each informational interval and the presence of pressures that can be used that are necessary to advance the flow in each area into high flow rate that can match requirements of production. QIMC now is entering phase 3 of the exploration program. Exploration, geophysical surveys are now being undertaken to provide additional data that would help to better orientate the direction of drill holes that should intersect the fractures and shears associated with the flow of hydrogen. Furthermore, 5 to 6 HQ diamond drill holes, 500 meters in length, are to be drilled at 45-degree inclinations. 2 holes in the West Advocate area, 2 holes in the East Advocate area, and 1 hole in the Southampton area, and possibly an additional drill hole in the Spring Hill areas if exploration budgets exist. Each hole is to be located at or adjacent to the maximum hydrogen anomaly on the road. It has been decided that these data to the edge of the road that will be collected in the future will give us some indications of where the higher values are, and therefore develop a vector that can point us in the direction and location of where maximum values of hydrogen are stored. Follow-up field samples on grid gather additional information that will be undertaken. Now, phase 4 indicates that following the completion of the 2026 winter program of phase 3, additional drilling is being contemplated. But again, we have to extend the spatial area of the faults and understand them better. More detailed geophysical surveys and modified reflection seismic surveys will be conducted on a grid adjacent to the anomalies being drilled. Again, the purpose of these measurements is to develop vectors of increase, decrease away from the anomalies, again, to point where we should be concentrating drilling activity of future drill holes. These data can help us to indicate anomalous sources and potentially its long-lived travel pattern. The objective is to locate in surface areas that may host hydrogen concentration of high volume. To meet these objectives, QIMC and INRS, to meet these latter objectives, QIMC and INRS have agreed to conduct the following additional surveys. Large-scale land-based gravimetric surveys across the West and East Advocate area to test the flow rates, pathways that are currently observed. Audio magnetotelluric AMT surveys, 17 kilometers in length, to map deep geological structures that may underlie hydrogen and radon-rich domains. High-resolution geoelectric tomographic studies to image in detail the fractured rock bedrock located immediately below the hydrogen-rich soil zones, and thereby provide additional information in evaluating structures. High-resolution ground-based time-domain electromagnetic studies, DTEM surveys will be used to locate the fractured corridors. As the data is accumulated and interpreted, additional deeper holes will be planned and located to verify the result. We plan these holes to be in the length of 1,000 meters. The angles are yet to be determined. Drilling will be the major cost component of this plan for stage 4. Phase 5 going forward, based on the success of the drill results obtained in these earlier phases, the objectives completely changed from finding the resource to developing the resource base, and essentially to defining the economic potential of the native hydrogen accumulation. This phase of exploration becomes a wholly new ballgame. The nature of exploration activities, the field and instrumental requirements, the nature of drilling, and the examination of results now will shift to those being experienced in the oil industry as they seek oil. Nova Scotia has had a long history of exploration for both oil and metals. In both instances, the perceived availability of experienced personnel, service companies, and especially appropriately equipped drill companies is a big plus for QIMC, and we are happy with this prospect. So the concluding remarks. I hope that you now have a better understanding of where QIMC is at in their native hydrogen exploration activities in Nova Scotia. I would also like to take this opportunity to thank the people of Nova Scotia for their warm welcome extended to my colleagues at QIMC and to make us all feel that we have a second home. I especially want to thank the advocate community for the service that we provided and all the people I have met with Natural Resources, Department of Mines, NOAA, and others, especially Danielle, Nicole, Andre, Rebecca, and Tim, for their assistance and help, and to my colleagues, especially to Mark Richer Lafleche, and to my two friends, Fred Bonner and Marco Zentilli, for their help and encouragement. Again, thank you all, and good luck in your activities.
I know lots of people were anxious to hear that presentation today. Do we have any questions that you might like to ask Ed before we break for lunch? Here's one.
Yeah, I got one here. Great presentation, thanks. Completely naive to the topic, I have to admit. But I'm curious, is there, it's really early in the game now, I'm sure, but you talked about the different stages there. Is there any indication on what it's going to take, size-wise, volume-wise, to get from stage 4 to 5 there? Like, what is the trigger?
Yes, we have, in order to undertake the activities, okay, we have first talked to all the landowners and seek their permission to work on their land. Most people, after explaining what we were doing, were not concerned about our activities, but some people expressed their concern because of their relation to the tourist industry. And we have to take this into consideration when selecting the areas for further exploration. Oh, does that answer your question?
I'm just wondering, is there any comparison to the Lorraine field in France here? What I'm thinking about is, what have you thought about as a maximum depth for your drilling that you think beyond that it's not worth chasing? And where my interest is with this is some past work that Dr. John Culler's done with the department, drilling for deep coal seams in the Athol area, the Franklin Manor area, actually, where we've had some really thick intersections of coal at quite considerable depth that really has never been followed up. In fact, that Spring Hill coal field, as it dips off to the west, it's never really been traced where the heck does this thing go. So I'm sort of wondering if you've got a number in mind that, like, beyond 1,500 meters, forget it, something like that. Any comment on that?
Yes, we did take that into consideration when we selected the area of our licenses. We selected them adjacent to the highlands, okay, and in fault zones that readily expose basement rocks. And we know that the fault on the northern boundary brings up basement rocks to surface, and that surface has been shown by all drilling to be less than 1,500 meters below surface. So we avoided the middle of the basin because, again, as you mentioned, it may be very deep. And the cost considerations, we have enough land where the depth of location, where the concentration may be located, should be probably less than 1,500 years.
Just for your information, I think this is a little known fact. There was uranium that was found in the Spring Hill area. I think it might have been back in the 60s or 70s. And the department actually issued a special license for exploration for that uranium. It might be worth something we're following up for you guys to see what those reports say.
You're better informed than I am.
I think this gentleman over here is next.
Hello, great presentation, thank you. You touched on seismic surveys briefly. How big is that factor in your toolkit in terms of finding the traps? Is it big or is it not your most useful exploration tool?
Sorry, can you repeat the question? Just a little closer to the microphone.
How important is seismic surveys